Good morning, everyone. Welcome to today's SNAP seminar. As most of you know, this is a virtual seminar on stochastic networks, applied probability, and performance that we started earlier this year. And this seminar covers the areas that are at the intersection of applied probability, society, and sigmetrics. So if you would like to receive our regular weekly emails about SNAP seminars, please join our mailing group. And as you all know, today we are very excited to host APS Markov lecture on SNAP. Um, so before I hand over to Ton, who is the chair of the Markov lecture committee, I just want to make two couple announcements. The first one is about question answers. So if you have any quick clarification questions during SEM's talk, please post on the chat box. One of us will be monitoring the chat box and will possibly interrupt the talk to ask questions. In addition to that, Sem is going to have one or two pauses in between his talk for questions. And we will have a question answer session at the end of Sem's talk. And we'll have a more elaborate discussion at the end of Neil's discussant's presentation. So over to you, Ton.
Thank you, Siva. So as many of you know, the Markov lecture is held every year at the Inform's annual meeting. And the lecture, as Siva mentioned, is selected by the APS Prize Committee. And this year, the committee members were Rami Attar, Rhonda Ryder, and myself. And this year's lecture is extra special because it is also a SNAP seminar. And on behalf of the committee, I would like to thank the SNAP organizers, as well as APS officers, because they have made this joint session possible today. And as the outgoing committee chair, it is my privilege to introduce the Markov lecture as well as the discussant. And this year's Markov lecture is Sam Borst. Sam has been a professor of stochastic operations research at the Eindhoven University of Technology since '98. He has also been a member of the technical staff at Bell Labs from '96 until last year. And Sam's main research interests are in the area of performance evaluation and resource allocation algorithms for large-scale stochastic networks, in particular computer communication systems. And he's particularly known for his work on queuing systems in which the workload has heavy-tailed characteristics, on scheduling with long-range dependent and self-similar traffic, and on possible instability of well-known scheduling algorithms in networks. In the domain of communication networks, his work has impacted wireless networks of several generations, call centers, packet data switches, medium access control, and content delivery networks. Fundamental and applied work, as well as their interplay, have been common threads throughout his career. His numerous awards include the Best Paper Awards from the ACM Sigmetrics Performance and Infocom conferences, as well as the 2017 ACM Sigmetrics Achievement Award. Sam, thank you for accepting our invitation, and we look forward to your talk. Before you start, let me also introduce the discussant, Neil Bolton. Neil is a reader in the School of Mathematics at the University of Manchester. He's also a fellow of the Alan Turing Institute, which is the United Kingdom's National Institute for Data Science and Artificial Intelligence. His research is in applied probability and has focused primarily on the decentralized minimization of congestion in networks. His research themes intersect with optimization as well as game theory. Neil is also a blogger, and he owns the blog appliedprobability.blog. He has won Best Paper Awards at the ACM Sigmetrics Conference and was also awarded the 2018 Erlang Prize by the Applied Probability Society. Neil, thank you as well for accepting our invitation. And now I would like to give the floor to Sam.
Many thanks, Tom, for the very kind introduction. I'm still a bit speechless, but let me say that it's a great honor and pleasure for me to give this lecture. And I would like to start with a few brief acknowledgements. First of all, I would like to also thank the organizers of the SNAP seminar, Christina, Reina, Siva, and the Bankur for hosting the talk today and for launching this very nice initiative in the first place. It's really been a shiny spot in the online reality of the last several months. I'm also very grateful to the APS Prize Committee for the invitation and for extending this tremendous honor to me. And also big thanks to Neil Walton for agreeing to take on this challenging task and being very patient with me over the last few weeks during the preparation phase. I would also like to thank my collaborators, Ellen Cardinaals, Johan van Leeuwarden, De Banker Mukaye, and Phil Whiting, for the joint work that the talk is based upon. And in fact, Ellen and De Banker have currently agreed to monitor the chat in case you have any immediate questions for clarification during the talk. And I've really learned that having fortune to find the right collaborators can make a huge difference in research. On that note, I would also like to mention a few further colleagues here in Eindhoven, Mark van der Boer, Celine Comte, Diego Goldstein, and Martin Zubaldia, for helpful discussions on various related topics that unfortunately I'm not able to cover today. Then I would like to mention two previous collaborators, in particular, Avi Mandelbaum and Marty Ryman, for introducing me to the wonders of scaling limits, among other things, which have really been very influential for me. And then finally, I'm deeply indebted to Onno Boksma and the Basis Mitra as long-term mentors for teaching me queuing and networking, and even keeping me sort of employed in the process. So with that, I would like to turn to the topic of the talk, load balancing in networked systems. And this topic falls right at the interface between the APS community and the Sigmetrics theory audience, and has been extremely active in recent years. In fact, it's been so broad and active that it's simply impossible for me to really cover all the results and threads in the recent literature. So I will focus on a few specific perspectives, but you can find a far more extensive list of literature pointers at the end of the slides, in case you're interested. So the problem is sort of illustrated here on the left-hand side. So we have a system with, let's say, n parallel servers, each with their own queue. And we have a stream of jobs arriving at a dispatcher that need to be immediately and irrevocably routed to one of the servers. So this is sometimes referred to as an output queued system, and this is a canonical model for data center operations. And I would like to contrast that with what you see on the right, where again we have a set of parallel queues, but now jobs are immediately queued upon arrival, and there's a shared resource that needs to be allocated among the various queues over time. So that is what I would refer to as scheduling or resource allocation in an in-queued system. And that model is more typical for call center assignment decisions, switches, wireless schedulers. And as you can tell from the pictures, there's a clear commonality and even duality, but throughout this talk, I will really sort of focus on what you see on the left-hand side. So here's basically the same picture, just to sort of carve that in your mind. Examples of these systems are supermarket checkout lanes, where it would be impractical to operate a single line. So you will see lines form at the various checkout counters. The only counterexample that I'm aware of is a Whole Foods supermarket in Manhattan, where they tried to operate a single line, and that didn't seem to work particularly well because it just gets quite messy if you have 20 parallel checkout lanes. And by the way, the model that I just showed is often referred to as the supermarket model, which is very telling, although in real supermarkets, there will be some features that are perhaps not captured in the model that people have considered. Road toll plazas are a further example where it would be impractical for all the vehicles to queue up in a single line. But then the application that has really sparked very strong interest in these models in recent years are data centers. So these are these sort of massive factory-like buildings stacked full with servers, thousands and thousands of them, where much of the online world sort of happens today. So the large-scale nature of these systems can both help and hurt. So it helps because it provides efficiencies of scale that can be exploited to improve the performance. On the other hand, if you really want to implement an optimal strategy in such a large-scale system, that might involve a lot of state information and overhead that is just not sustainable in a large-scale system. And that sort of brings me to sort of the challenge here, which is really to achieve excellent delay performance, and resource pooling is key to that, while only requiring low complexity and implementation overheads in a large-scale system. And that's where scalable algorithms come in. So that would explain the two subtitles to the talk. So here's a high-level outline of the talk. I will, in the first half, focus on the supermarket model and discuss various recent results in that area. And then in the second part of the talk, I will move beyond the supermarket model and focus on issues like heterogeneity and compatibility constraints. So let's start with the supermarket model and some assumptions that are quite strong, but will be convenient definitely for the purpose of the talk. As I mentioned, I will focus on systems with n parallel servers with an aggregate service rate n times mu. So mu is the service rate normalized by the servers. Tasks arrive as a Poisson process of some rate lambda n. There's just a single dispatcher. Tasks just entail a single piece of work, no task graphs or anything. The processing requirements are independent and exponentially distributed with unit mean. We have no advanced knowledge of what the processing requirements are. And I also assume that the transfer of messages and tasks between the dispatcher and the servers is instantaneous. So all of these assumptions could or probably even should be argued with, but for the purpose of the talk, this is what I will stick with for most of what I will describe today. Now, coming back to the large-scale operations in data centers and many of these systems, I will look at the behavior through various asymptotic regimes. And perhaps the regime that most of you are familiar with is the classical heavy traffic regime, where the load, the arrival rate, approaches the service capacity in the limit. But most of the talk will actually focus on somewhat different regimes where the number of servers grows large. So n tends to infinity, and the loads may also be scaled jointly with the size of the system in the manner that you see here, where in particular the parameter alpha is very important. So alpha is 0, means that the normalized load per server remains constant as the system grows large. And I will often refer to that as the large capacity or the large N regime, or quality driven, if you want to think of it from the call center perspective, perhaps. Alpha is 1/2, corresponds to the halving width regime, where the total capacity slack is of the order of square root of n, also known as the QED regime. Alpha is 1 is a more recent regime that has been considered, referred to as non-degenerate slowdown, where the capacity slack tends to a constant in the limit, also sometimes referred to as efficiency-driven regime. And then there are several further regimes for intermediate values of alpha or even larger values of alpha that have been considered in recent literature, but I will not have the time to really elaborate much on that today. So let's start with some classical results and scalability challenges in the context of the supermarket model. So here's now the system that we are looking at. We have a flow of arriving tasks as a Poisson process of rate n lambda, and servers, each with servers rate mu. And one very simple assignment scheme would be to just flip a coin for every arriving task and assign it with equal probability to any of the servers with probability 1 over n. So that would create n independent Poisson arrival processes, each with rate lambda, and that in turn would make the system behave as a set of n independent MM1 queues, each with arrival rate lambda and mu. So here's the real problem that we're interested in, how to optimally assign these incoming tasks. And one simple, reasonable way to do that would be to apply strictly random uniform routing, which would give rise to n independent MM1 queues. And what it would mean is that the total queue length in expectation would scale with n, and the waiting time, expected waiting time, would not depend on n at all. Okay. Now, on the other hand, suppose that we could operate a centralized queue. So that is often prohibitively complex, but suppose we could, that would give rise to an MMN queue. And again, we can calculate the expected queue length, the expected waiting time. And what we see is that the expected waiting time is smaller by a factor n, at least. And remember, n is the number of servers. So in a data center, that could be 1,000, 10,000, 100,000. So even though this situation on the left looks quite reasonable, at least the waiting time doesn't get worse as the system scales. There's a lot to be gained if we could move closer to the operation of a centralized queue. So that raises the question, how close can we really get? And how much would that take in terms of complexity? So a natural policy to consider in that regard is join the shortest queue, which does exactly what the name suggests. When a job arrives, it is sent to the shortest queue, ties being broken arbitrarily. So next job arrives and it goes to what is now the uniquely shortest queue. So to look at the behavior of that, the maybe most obvious state description would be to just keep track of all the queue lengths at the various servers. But what is often convenient is to rearrange the queues in increasing or decreasing order from left to right, and then look at the widths of the horizontal bars in the picture that you then obtain. So Qi here is the width of the ith horizontal bar, and it represents the number of servers with a queue length I or larger. And because of the symmetry, this system occupancy vector is a Markov state descriptor. So that's very convenient. And it provides a very convenient basis for many server scalings, while it can still be used to infer what the queue length is at individual servers. So this turns out to be a very convenient state descriptor for situations where n will grow large, because the dimension of the state descriptor will not be affected by that. In particular, we can now define what are called fluid scaled state variables, where we divide by n the total number of servers. So that would then provide us with the fraction of servers with a queue length of I or larger. And any weak limit of that process in the large n regime, we would call a fluid limit. And it turns out that the fluid limit has a remarkably simple fixed point, as is illustrated in this picture here, for the join the shortest queue policy, where we would just see a fraction lambda of the servers having exactly one task that they are processing, while the remaining fraction 1 minus lambda is idle. So that is really very informative. It's perhaps a bit crude, so it also makes sense to look at a somewhat more refined scale, the diffusion scale, where we look at these state variables on a square root n scale. And if we do that, we can also look at diffusion limits, weak limits of the process that is scaled in that way. And that diffusion limit for the joint shortest queue policy was characterized by Eschenfeld and Gomarnik a few years ago. And you see the description of the diffusion limit here. What is maybe already sort of coming through in that description is that it's very similar to the diffusion limit for the centralized MMNQ. If you look at the total number of jobs, Q tot, and the vacant number of servers, Q vac, then that looks almost exactly like what you would see in an MMNQ, except for that term highlighted in red, the Q2 bar T, which arises from the fact that the joint shortest queue policy is not work conserving. It can happen that sometimes there are some jobs waiting at some servers, while other servers are idling because these routing decisions are made in an irrevocable manner. But what it does show is that the joint shortest queue policy lives sort of on the same square root of n scale like the MMNQ. So in that sense, it is nearly as efficient as a fully pooled operation. Then there's also an interchange of limits that was established by Braverman a few years ago, so that we can also think of this as an indication for the steady state performance. And further equilibrium properties of the diffusion limits were analyzed in separate work of de Bancour also in recent years. So based on that, we can see how well joint shortest queue does. And it really yields huge improvements over purely random assignment. So it eliminates queues. We only see servers with 0 or 1 jobs. It achieves a 0 weight, both in the large N regime and in the health and width regime. And in fact, it matches the scale that we would see in the centralized MMNQ, except that the prefactor is different and a little larger. But there's a but that if we look at the overhead that is involved, if we use a straightforward implementation of the joint shortest queue policy without any memory, we would need to check all the queue lengths for every arriving job, and that might simply not be sustainable in large-scale systems. So that observation motivated very strong interest in joint shortest queue D policies, where we only sort of check D queues when a task arrives, and we send the job to the shortest queue among these D servers. And in case of batch arrivals, the overheads of the queue samples can be even reduced further by amortizing it across multiple tasks. Okay. So this policy was already analyzed in the 90s in very important work by Ferenskaya and Mitzenmacher, who derived the fluid limit for this policy in terms of the set of differential equations that you see here. And it turns out that these differential equations have a very nice fixed point, which you show here for the fraction of servers with I or more jobs. And again, we have an interchange of limits. So we can also think of this as the stationary queue length distribution at an individual server in the large N limit. And what we see is that it falls off much more rapidly for any value of D larger than 2 than the geometric tail distribution that we would see for an MMNQ. So that is often referred to as the power of 2 effect. And then there's even results for the diffusion limit, which were obtained by Eschenfeld and Gomarnik a few years ago. So to summarize the joint shortest QD policy, it involves much lower overhead. We would only need to exchange 2D messages per job between the dispatcher and the servers. It provides way better performance than random assignment. We see the super exponential decay of the queue length distribution, but there's a but, namely, it is not strictly optimal in the limit. So the waiting time does not vanish in the large N regime. In the health and width regime, the queues even grow with N. And in a way, this is not just something that is bad about join the shortest queue policy, this is inevitable. There has been very important work by David Gomarnik, John Tzitziklis, and Martin Zubaldia, which showed that without any memory at the dispatcher, in order to achieve zero delay in the limit, it is inevitable that the communication overhead must grow with the size of the system. So let me briefly pause here to see if there are any urgent questions before I proceed. Okay, if not, then let me move on. So this is what we just saw for join the shortest queue D policies, with random routing as one extreme, where we see the geometric tail distribution of an MM1 queue, and join the shortest queue on the other side of the spectrum, where basically the queues have vanished. And that raises the question, so what happens in between? And in order to examine that, we have considered scenarios where the diversity parameter D is a function of n, and we write sort of dn to reflect that. And what can then be shown is that as long as dn grows large with the size of the system, the corresponding fluid scaled process has the same limit as ordinary join the shortest queue policy. So the same sort of stark picture that you see here at the bottom, which means that the fluid level behavior coincides with that of the join the shortest queue policy, as long as dn tends to infinity at any rate. Or you can also look at it as saying that the join the shortest queue dn policy achieves fluid level optimality while reducing the communication overhead by nearly a factor order n compared to the n messages that you would need to exchange under the full join the shortest queue policy. And that can also be extended to the diffusion limit, except that now dn must grow at a particular rate faster than squared n log n in order for the diffusion process to have the same limit as the ordinary join the shortest queue policy. So that shows the same diffusion level behavior, and also that the communication overhead can be reduced by a factor of almost squared n over log n while retaining the diffusion level optimality. That condition is also more or less necessary. If you try to get away with less, then the limit would differ from the ordinary join the shortest queue policy. And in recent work, there have been results for arbitrary growth rates of dn, showing a very strong trichotomy depending on how fast dn grows relative to square root of n. So that provides us with this picture that we saw before, and that there's really a very strong universality and asymptotic optimality for a whole class of join the shortest queue dn policies, as long as dn grows large. And if dn grows faster than square n log n, we see the same behavior for that entire class of policies on the diffusion level, implying diffusion level optimality. So that adds 2 rows to the table, where we see that for growing dn, we can achieve the same performance in terms of queue lengths and waiting times as the full join the shortest queue policy. And the overhead, you see some sort of yellow pinkish color there, because it is much better than the red associated with the join the shortest queue policy, but it does grow with n. And as we saw already, that is inevitable given the results of Gomarnik, Tzitziklis, and Zubaldia. And what it also tells us, that result, is that the only way to get around it is to leverage memory at the dispatcher. And that's exactly what the join the idle queue policy does, which pretty much does what the name describes. It assigns jobs to idle queues. So that can be implemented through tokens, where when a server becomes idle, it sends a token to the dispatcher, and then the next server becomes idle, also sends a token to the dispatcher. When a job comes in, the dispatcher takes the token and sends the job to the corresponding server. Okay? Until, of course, at some point, there are no tokens left, And at that point, the jobs are assigned to any of the servers uniformly at random. Okay, so note that tokens are only generated upon service completion when a server becomes idle. So at most one token per task, meaning that the communication overhead is constant by design. And it turns out, this was shown in work of Stoljar, that the fixed point of the fluid limit is exactly the same once again as it was for join the shortest queue. So a fraction lambda of the servers have exactly one job, a remaining fraction 1 minus lambda of the servers is idle. So that's again very telling. It's a little crude, so we can also look at the diffusion level behavior. And it turns out that the same situation applies there, that the join the idle queue policy has the same diffusion limit under suitable initial conditions as the ordinary join the shortest queue policy. So we see that the join the idle queue strategy really outperforms the join the shortest QD schemes in terms of performance and communication overhead, because the latter policies cannot both achieve zero delay and have constant overheads for any single value of D in the limit. Okay. Now, of course, the way that is achieved is by exploiting memory at the dispatcher. And we know from the results of Gamarnik, Tsitsipas, and Zubildia that that is necessary. Once you observe that, though, you realize, well, perhaps we could even have implemented during the shortest queue by keeping memory at the dispatcher, and that is true. So what the result maybe really says is that there is no need strictly for such fine-grained queue length information, that just distinguishing between the busy or idle status of the servers is sufficient to achieve asymptotic optimality. Okay. So that provides us with this table now with an additional row for the join the idle queue scheme, where all signs are green now, but note that memory is not captured in this table. So that is what is needed to achieve that. There's a further caveat that the diffusion limit shows that similarity between join the idle queue and join the shortest queue. But if we were to consider a classical heavy traffic regime, join the idle queue would collapse and it would degenerate into a purely random assignment. In fact, even in the non-degenerate slowdown regime, join the idle queue already triggers a lot of random assignment decisions, which yield a different occupancy process than join the shortest queue. And there has been very nice work by Neil together with Varun Gupta, who developed a strategy that also distinguishes between queues of size 1 or larger. And with that enhancement, the strategy does reproduce the same asymptotically optimal occupancy process as join the shortest queue. And I guess the broader message in that work is that these alternative asymptotic regimes, even if perhaps you might not find them plausible from a practical perspective, they can allow you to distinguish more sharply among different assignment strategies. Okay, so that concludes the first part. Let me again briefly pause to see if there are any urgent questions to be asked. Steve, I think you're muted.
Yeah, I have a question, a clarification question. So when you say fluid model, fluid limit, you mean the mean field regime when lambda is fixed and n goes to infinity, and the
Yes,
diffusion limit is the half-infinite regime, right?
That's right, yes. So I use fluid limit where maybe I should have said mean field limit. I think fluid limit is, strictly speaking, when you have a system of fixed size where the initial state grows large, which has some similarity with the mean field limit, but yes, that would be the better term, you're right.
And if I may ask, why is it that you're focusing on these two particular regimes? Because you showed a table with many, many regimes. So early in the talk. So why is it that these two are important?
Yeah, that's an excellent question. And to me, the mean field regime would seem the most natural for data centers, since utilization is typically not very high. Of course, you could argue we should look at peak periods where utilization could be higher. So that could be a reason to also bring in some heavy traffic notion in the scaling regime. And perhaps to the point of what I was just saying, an additional reason for considering alternative regimes is to distinguish in a more sort of fine-grained manner between various strategies. Because the mean field regime, you could argue, sort of collapses many strategies into the same universality class, which is nice in a way, but perhaps it's a little bit crude. So I think there's definitely merit in considering all the intermediate regimes for alpha values between 0 and 1/2, 1/2 and 1, and perhaps even the super heavy traffic when alpha is larger than 1, definitely.
Thanks.
Okay, thank you. So let's switch gears and move now beyond the supermarket model to models that account for heterogeneity and compatibility constraints between jobs and servers. So a very fundamental premise in the supermarket model is that any job can be handled equally well by any server. Now, in practice, of course, servers may be heterogeneous, and even when jobs and servers are not intrinsically different, it may still be the case that some servers are better equipped to handle particular jobs than others because of data locality and topology constraints. So here you may want to think of sort of the huge data sets that are involved in many applications that run in data centers, where not all data is stored on all the servers, nor is it stored in a single centralized site. So it is replicated selectively among subsets of the servers. So that means that the time that is needed to retrieve the data that is needed for streaming or processing a job will vary depending both on the kind of the job and the location of the server. And that sort of introduces a asymmetry among the servers and immediately breaks sort of the fundamental underpinnings of the fluid and diffusion limits. And also the stochastic coupling arguments that I didn't really discuss, but that are the engine behind many of the universality results, which really hinge on that symmetry among the servers. In fact, it's even worse that the system occupancy is not even a Markov process anymore when that symmetry between the servers is lost. That creates an immediate obstacle to many server scalings, unless there's still some very strong form of symmetry or a limited degree of heterogeneity that doesn't grow with the size of the system. So let's now look at that. And here's a first attempt to tackle some of these issues where now the end servers are arranged in some graph topology, GN, and jobs arrive at any of the servers, let's say at some rate lambda, and they can either be processed locally or they can be forwarded to any of the neighbors in that graph. So that locality could be due to some network topology. If you think of racks in data centers, it's also very reminiscent of one of the first problems I worked on at Bell Labs, routing in geographically distributed call centers together with Marty Ryman and Judy Siri, where perhaps the numbers of nodes were not as large as you would think, as you would see in a data center, but in terms of the network topology, it was very similar in nature. So here a job arrives, and then the server checks with its neighbors, and it forwards the job, in this case, to one of the neighbors with a shorter queue. Okay. So that raises the question, how do the graph properties in terms of density and structure affect the performance that jobs experience in terms of queue lengths and delays? It's probably good to also look at a special case of a fully connected graph. So then when a job arrives, all the servers are checked. So that corresponds basically to the ordinary supermarket model that we saw before. Now it turns out that the case of regular graphs, in particular ring topologies, already received some attention as early as the 90s by Stephen Turner, who was a PhD student in Cambridge, and also more recently by Nicolas Gast. So here, in case of the ring, every server would check with its two neighbors in the ring and forward the job to a neighbor with a shorter queue if that's the case. And what their results suggested was that join the shortest queue in this deregular graph shows worse performance than join the shortest queue D policies in a complete graph. So even though the same number of servers is sampled, performance is worse because we sample essentially from the same subset again and again, rather than completely randomized across all the servers in the entire network. So that's also means that the performance is very sensitive to what the exact graph structure is. So the angle that we took was to basically take the perspective of the universality that we saw in the context of the ordinary supermarket model and ask the question, how much connectivity do we really need in order for join the shortest queue to produce the same performance as in the complete graph, namely the basic supermarket model? Or equivalently, how much sparsity can we allow while still retaining the asymptotically optimal performance of a complete graph? There's a slightly different universality criterion, which is basically asking that question, but not for join the shortest queue, but for join the shortest queue D, and that has been pursued in separate work of de Bancourt. So this turns out to come down to conditions on neighborhood sets in the graph. And there are two conditions in terms of the size of the neighborhood of any group of order n or order square root n of vertices being very close to n up to a little order n or little order squared of n margin. And then we can say that a graph sequence is now fluid optimal or diffusion optimal if it yields the same fluid limit in the large n regime or in the half and width regime as for the complete graph. And then it turns out that if condition 1 is satisfied, then the graph sequence is fluid optimal. If condition 2 is satisfied, the stronger condition in terms of the neighborhood sets, then the graph sequence is even diffusion optimal. These results actually come a little cleaner and more transparent in random graphs, where the structure is, for example, described by an Erdős-Rényi random graph or a regular graph. And in that case, the conditions can be stated purely in terms of the degree or the average degree. And we see that the graph sequence is fluid optimal as long as the average degree grows to infinity, and diffusion optimal if the average degree grows faster than square root n of log n. And notice that this mirrors exactly the conditions that we saw before for join the shortest queue dn policies in the original supermarket model. So the takeaway is really that the performance of a fully flexible scenario can be matched in relatively sparse graphs. And I don't mean with finite degree, but graphs that are way, way sparser than the complete graph, provided the structure is suitably random. Okay, I will now turn to more general compatibility constraints beyond the graph-based models, and note that in the graph-based supermarket model that I just described, we can think of there being n types of jobs, each with the same uniform arrival rate, lambda n over n, corresponding to each of the servers. So that covers locality of servers with respect to some network topology, but it cannot really capture the more general compatibility constraints that can arise from locality of data objects, for example, files or content items that are only stored with arbitrary subsets of the servers. So to capture that, we can look at an extension where the job types now correspond to arbitrary subsets of the servers rather than individual servers. And the way you can think of these subsets are as the group of servers where the data is stored to serve a particular kind of job. Let's say that the collection of jobs is denoted by calligraphic S, so all the subsets that have a non-zero arrival rate associated with them. And then that compatibility structure can be represented in terms of a bipartite graph between, on the one hand, the servers, 1 through n, And on the other hand, all the job types corresponding to subsets of servers, namely the neighbors of that type in this bipartite graph. Okay, so this is now clearly more general than the model before, where we basically identified the types with the servers. This is way more general and can describe arbitrary compatibility constraints. And in addition, we'll now also allow for heterogeneous server speeds. Then there are some very natural stability conditions that are necessary, which basically say that if we look at any subset of the types and we look at the servers that could potentially handle these job types, their aggregate service rate should be larger than the total arrival rate of these job types. Or you can flip it around and say, if we look at any subset of the servers, the total arrival rate that they need to handle that can be served by these servers only must be less than their aggregate service capacity. So these are necessary conditions, and for most reasonable strategies, they would also be sufficient. Now, in terms of that compatibility structure, we can look at, again, a fully flexible system where all jobs could be handled by all the servers. So that's basically corresponds to just a single job type that is connected to all the servers. And that will provide us, again, with some performance benchmark, that what is the best that we can hope to achieve. And in that case, the stability conditions reduce to what you would expect, that just the total arrival rate should be less than the total service rate. Now, what is also, I think, important here is to think of a slightly different way to describe this model, where we have a total arrival rate of jobs lambda tot, which is the sum of the lambda s over all the types, and an arbitrary job being compatible with the servers in S with some probability PS, which is the lambda S divided by lambda tot. So that is equivalent because of the splitting property of Poisson processes. And with that perspective, you can see that power of D policies are basically captured here as a special case. So power of D policies usually are not really directly related to compatibility constraints, but rather to the need to limit the overhead. But you can think of them as having a certain compatible set of servers, namely those servers that are sampled for a particular incoming job. So note that power of these settings are captured as a highly symmetric special case within this framework. And then you can also specialize the stability conditions for these scenarios, and it boils then down to just an upper bound for the total arrival rate. Okay, and then maybe to make it a little more confusing, but I'll return to that in just a moment, this refers to a power of D policy in a fully flexible scenario, but in fact, you can run a power of D policy on top of any compatibility structure. So this is now the problem that we end up with. So we have an arbitrary compatibility graph, and we want to look at good load balancing strategies in this context. So here, a job of type 3 arrives, and we have to decide where to route it. In this case, maybe to Q4. But the question is, what is a good strategy for this in general, taking into account the compatibility constraints, the various server speeds, etc., etc. So there have been some breakthrough results in these kinds of models recently. Work by Daan Rutte and De Bancour, who considered the above setup, I believe, with uniform arrival rates for the various classes and homogeneous server speeds. And they establish process level limits, which show that the join the shortest QD policy on top of certain graphs produces the same behavior as in a fully flexible system. And that entails certain conditions in terms of the graph G, which they describe as proportional sparsity. There's also been some very nice work by Rentaro Wang and Zhao and Shrikant, which in fact Shrikant presented in the SNAP seminar in early August, who do allow for arbitrary arrival rates and heterogeneous server speeds. And they look at steady state performance using drift methods to prove that speed-aware extensions of join the shortest queue and join the idle queue can match the performance of a fully flexible system as n grows large. And again, that involves certain well-connectedness conditions in terms of the graph G, as well as now the arrival rates and server speeds, since they are now heterogeneous. And what is remarkable is that these graph conditions are of a similar flavor as the ones we saw before in the supermarket model on a graph structure, though obviously more intricate because of the additional heterogeneity in server speeds and arrival rates, as well as the more general bipartite graph. But what it shows is that, again, the performance of a fully flexible system can be achieved even in relatively sparse compatibility graphs, provided they have the right structure. And this really expands the universality properties of join the shortest queue DN policies, which are included here as a very special case in a way, with highly symmetric properties. Then in the last 5 minutes, I will continue with these models with arbitrary compatibility constraints between job types and servers, but I will move now from the many server scalings to a more classical heavy traffic regime, and I will also move from queue-based assignment strategies to redundancy policies. Okay. So the setup is the same. We have these job types that correspond to the various subsets of the servers, but now rather than selecting a single server upon arrival, replicas of a job are assigned to all the servers in the subset S for a type S job. And then we'll distinguish two scenarios depending on when replicas are discarded. We can either do that the moment the first replica completes service, that we discard the remaining replicas, or we could already do that the moment the first replica starts service. So that is referred to usually as the cancel on completion and cancel on start mechanisms. Now, this might seem somewhat of a different setup from the join the shortest queue, join the shortest queue D, join the idle queue strategies, which are all queue-based. But the rationale here is that they are closely related to these policies while being analytically tractable, as I'll show in just a minute. So in fact, the cancel on start version basically emulates a join the shortest workload policy, where the type S job would be assigned to the server with the smallest effective workload. That's in essence what happens under a cancel on start policy. And in turn, the join the shortest workload policy strongly resembles a join the shortest queue policy, modulo perhaps speed-related factors, but it's really looking at queue lengths or workloads. So that has a very strong similarity, and I will give some pointers later to support that claim. And in addition, as I mentioned, we'll now turn away from the many server regime and look at the classical heavy traffic regime. So here's the setup for cancel on completion. So here a type 3 job arrives, and we place 2 copies in the queues of servers 2 and 4 that correspond to type 3. And it turns out that the state occupancy process has a product form distribution, which is, I think, quite remarkable for completely arbitrary compatibility constraints. And I don't even have the time to explain the notation in detail here, let alone sort of discuss where these distributions come from. But I would like to refer to a very nice tutorial that Utsi Ayesta gave just last week at a performance conference. And there was also an overview talk by Christy Garner and Rhonda Reiter at the APS conference in Brisbane last year. So these are explicit distributions of a product for nature, or very detailed state descriptions. So that is great. The one sort of issue is that they do not immediately provide much insight in how the structure of the compatibility graph affects the performance, because that only comes in implicitly through, for example, these mu coefficients. There's similar results for the cancel on start version. So here again, let's say a type 3 job arrives and we place 2 copies in the queues of servers 2 and 4. The difference here is that for the same arrival sequence, some copies would already have been cleared, because that happens in this case the moment the first copy enters the service. Again, there are product form results for cancel on start mechanisms, which are slightly more involved, but again, they are explicit, and now they also need to keep track of idle servers, because that makes a more significant difference in the case of cancel on start. So these product form distributions provide a basis for further analysis. It's not immediate, because they are for very detailed state descriptors, not just in terms of the numbers of jobs, but we can take them for further analysis by aggregating over all these very detailed states to obtain queue length distributions. And in order to do that, we impose some further conditions on the probabilities and the arrival rates and service rates, which essentially mean that all the stability conditions are satisfied as long as the total arrival rate is less than the total service rate. That's not very critical, but it just makes it a little easier to state the results. And then it's also convenient to introduce a lambda and a mu again, even though the arrival rates can now be heterogeneous and the service rates can be different. But it's easy to think of lambda and mu as the arrival and service rate normalized per server. And with that, we can look at heavy traffic limits. So that involves moving from that very detailed state description to summing over all the states with the same total numbers of jobs, taking generating functions. And if we do all of that, we can prove a state space collapse for these redundancy policies, which show that the vector of queue lengths of various types behaves exactly like it would in a multi-type MM1 first come first served queue, with arrival rates n lambda, service rate n mu, and type probabilities PS. And this in fact mirrors some process level limits in work of Rami Attar and others for not the cancel on completion version, but the cancel on start, which again is very close to the join the shortest workload policy, and also results of Siva and Daniela Hurtado-Lange for join the shortest queue type policies in power of these settings, where they observe similar state space collapse results. And these results also translate to waiting times and sojourn times, where we find exponential distributions as limit laws. And what is remarkable here is that these distributions for the sojourn time and waiting time do not depend on the probabilities PS, the type probabilities, at all, as long as the local stability conditions are satisfied. And also, all the types see the same waiting time and sojourn time in the limit. So whether a type is compatible with just a few of the servers or many, it makes no difference in the limit. So perhaps some further observations along these lines. So again, we see a remarkable universality now in a heavy traffic regime rather than the many server scenario, where the system achieves full resource pooling and the same behavior across a broad range of scenarios, as long as there are no local capacity bottlenecks. And as I already alluded to, there's no real difference in this limit between having a system with many job types, each having very limited flexibility, or systems with only a few job types and having great flexibility. We also see the results that was already shown by the work of Rutten and Mukaye and by Wang, Zhao, and Shrikant, that the performance of a fully flexible system can asymptotically be matched even with quite stringent compatibility constraints. So if you translate that back to the data center applications, it means that a fairly limited degree of replication would already be sufficient to achieve full resource pooling, as long as it's done right, the right amount and the right servers given the load distribution. Adding greater flexibility will only provide limited gains, but it might help with robustness, especially if there are uncertainties about the speeds of servers or the relative proportions of loads among the various types. So with that, let me sort of conclude with a few further extensions and possible future directions. As I already alluded to at the start, any of the convenient assumptions that I made for the purpose of this talk could and probably should be relaxed. Autoscaling, dimensioning, learning paradigms, they're very natural and important topics, and I just didn't have time to really say much about them today. I was sort of focusing here on universality within join the shortest queue, DN policies, and within the class of redundancy policies. But as I was alluding to, there might also be universality across these classes, join the shortest queue, join the smallest workload, and redundancy. And I think the similarity of the results of Attar and Hurtado Lange and Siva, and what we found here for redundancy, is a pointer in that direction. Of course, there are some different asymptotic regimes. There are sort of the many server scenarios with graph conditions, and then the graph conditions in the heavy traffic scenario. It would be nice to connect that, maybe also look at joint scalings to see if there's some unifying pattern that would emerge from that. Then there is a trade-off between sparsity, or maybe I should say the cost of replication on the one hand, and the degree of robustness on the other hand, if there are mismatches or swings in the load distribution among different types. And then finally, these models that I described allow for quite general compatibility constraints, but we could take that one step further and even allow for completely arbitrary service rates depending on the job type and the server. So with that, I would like to thank you for your attention, and then probably pass the token to Neil. I'll let him explain what you see on this slide, unless there are any immediate questions now. Otherwise, we can take them after the talk of Neil. So if not, then I guess I'll stop sharing and Neil will take over. Is that okay, Siva?
Yeah.
Okay.
Okay, I'll start sharing my screen here. Okay, can everybody see my screen now? Yeah. Good, great, thank you. And I'll just pop everyone up here so I can kind of see people's faces a little bit as well. So I think what Sem was referring to there was, so that was a paper by David Lindley in 1952, which I was pointing out to Sem whilst we were discussing the sort of the talk and all the rest of it. And I mentioned that, so when Kendall first introduced the kind of MM notation, that was like a kind of Royal Society lecture, and then Lindley was the discussant, and it was from the discussant part where Lindley's recursion comes from, basically. So thanks, Sam. Like, there's not going to be no Lindley recursion or anything like that here, that's for sure. Yeah, you know, in fact, you know, if anything, I mean, you know, from watching like Shrikant's talks, I also kind of watched on YouTube Anna's talk, and also Balaji Prabha's. I'm sort of quite humbled by the kind of level of expertise across the kind of APS community, and obviously massively by Sem as well, who's a kind of real stalwart amongst that. So with a massive amount of kind of humility, I'm going to kind of try and stick to what I know, and also given you've just sat in an hour-long talk, I'll try and keep it reasonably lightish as well. Yeah. So one thing I'll mention at the very very start is, also mentioning kind of a little bit older papers as well. Yeah, I didn't realize it's going to mention the Lindley thing. Essentially, it's a classical problem of how many servers you're going to have given the number of jobs that are arriving. That's something that goes right back to Erlang in sort of 1917, sort of one of his first papers. And in that paper, he quotes that, from a 1914 paper on the number of selectors in automatic telephone exchanges. And so it really is kind of one of these things that's been around in queuing basically since the start. Is one of those problems that's never going to go away, and there are always going to be kind of new aspects to it that people are going to want to investigate. So a good answer to that question of how many jobs you should, how many servers you should have, sort of was answered partly in sort of the Halfin-Witt paper in 1981, and then sort of in the early 2000s, you have the kind of QED regime giving kind of precise way of saying how many servers there should be. And it's worth remembering that Sem was, one of the authors on that paper, along with Avi Mandelbaum and Marty Reimann. I think there's, as Sem's pointed out, there's an increased interest in these kinds of models because of their use in data centers. And that also brings a slight shift in the narrative, going away from how many servers we should be having, given the number of jobs that are arriving. And we've moved on to something where we're looking at how many jobs we should be having, given the number of servers that are available, if you see what I mean. So we're starting to think about replication and how many available jobs we should have in our system. Okay. So I was going to discuss two aspects of Sem's talk. There were two aspects there. So the first part is on kind of load balancing and scaling regimes. The second part is on reversibility and product form and these kind of results on redundancy scheduling. The first part is something I've worked on sort of proactively. The second part I haven't really worked on, but I just think it's kind of a cool area, and I'll kind of add some thoughts on that. Okay. I've just realized my pen's run out of ink, so we'll see how I get on without my laser pointer now. Looking forward to trying it out, but anyway. Okay, so so the first part on role scaling regimes. The first point to say is here at the top, and in the first picture there you see two parallel queues with parallel servers which are working independently on jobs that are arriving at the same rate. And you're going to get twice the queue size you get from two single server queues. Okay. In the middle, we have something where we've pulled things together into a central queue, and we can write down the queuing formula for that as well. Okay. And we can see we get an extra help of 1 plus row at the bottom of the denominator there. And then finally, in the final picture on the right-hand side, top right-hand side there, we have the system where you've got a single server that runs at twice the speed, and you get twice the benefit. Okay. The point of including that picture is that when we talk about things like resource pooling, we often talk about them as scaling regimes, but it's worth noting in those pictures there, particularly the middle picture, that you don't need to be taking any limits to be seeing a lot of benefits from doing resource pooling. It's something that really happens in the pre-limit. Okay, it just gets kind of highlighted and exacerbated and more pronounced as you go into the limit. But even for very small systems, you're going to see a lot of benefits from resource pooling. The second point here is that at the bottom here is if we do have many parallel servers, okay, and you have an arrival rate per server row, then we're going to have about row, if the system's stable, row of those servers is going to be serving in equilibrium. So you're always going to have 1 minus row servers which are empty. So it doesn't matter what service rule you're using or dispatch rule you're using, you can expect about 1 minus row of the servers to be idle at any point in time. So as you see sort of highlighted in gray at the top here, in some sense it doesn't make sense to have jobs up at the top. If you've got a well-provisioned system, you're always going to have a kind of row of servers which have only got 1 job at them, and then 1 minus row servers with no jobs at them. Okay, and you know, in call center systems, you don't want capacity to get wasted, and so you're starting to reduce the number of servers in order to deal with the cost of having the servers there. And in data centers, we're starting to see an increase in the number of jobs to make use of that capacity as well. So that's a counterpoint there, though indeed many data centers are, by and large, most of the day very, very well or quite over provisioned. Okay. So one of the points that Sem went into was a bit about kind of universality properties, particularly universality of, say, drawing the shortest queue in the Halphin-Witt regime. So the Halphin-Witt regime, the formula is given at the top for the Halphin-Witt regime, but ultimately what it means is the free capacity that you're going to have is about 1 over square root of n, or square root of n, should I say, 1 over square root of n when scaled, square root of n when unscaled, where n is the number of servers in the system. Okay, and so essentially what happens under that Halphin-Witt regime, which is the regime you want to consider if you're going to optimally kind of provision the system, is that all of the queue lengths are essentially of length 1, except for a small amount of error of about the order square root of n where there are idle servers. Okay, and that's what we see in the kind of analysis of Eschenfeld and Gamarnik, and also in Braverman, looking into the interchange of limits in that, and also in the work of Mukherjee, Borst, Van Waarden, and Whiting as well. And what we find when we're looking at drawing the shortest queue, it acts as a kind of good example of what that behavior should be like. And so when we're looking at things like drawing the idle queue, which Sem talked about, or other of these kind of idle-based scheduling and dispatch rules, is that many of these policies end up having the same behavior in the limit when we look at them in the these kind of universal or Halphin-Witt or mean field or heavy traffic scaling regimes. So a lot of policies have similar behaviors when we apply a scaling regime to them. Okay, so I think the kind of main reason Sem sort of asked me to help out with the discussant bit was to discuss essentially the case of the kind of non-degenerate slowdown regime, which is a case where there isn't necessarily this universality property going on. And there are reasons why we might start to think about slightly heavier than Halphin-Witt regime scalings, okay? So essentially the non-degenerate slowdown regime was sort of, the term is given by Rami Attar in 2012, and he was kind of interested in call centers and kind of noticed that there tends to be much larger waiting times for access to call centers than maybe typically modeled. A kind of range of scaling regimes were considered by Ward-Witt and Itai-Gurvich earlier, which would have included the NDS regime. And then sort of Rami Attar had some discussions, I think, with personal communications with Avi Mandelbaum about that. It's also something that came up in 2017 with Kostas Malgaris, Yao, and Asaf Zivi, where they were looking into a model where there was a kind of cost for waiting, essentially. And then Varun Gupta has been a kind of real stalwart of this kind of idea and pushing this forward. And myself, who worked on this in the context of load balancing, be very keen to kind of advocate it as approaching a load balancing regime. So what does non-degenerate slowdown regime mean? Well, it's where the kind of gap, the number of idle servers you see in this picture is a constant, okay? So it's the scaling regime that means that the amount of idleness in the system is of the order of a constant. Now, what does that mean in terms of the system behavior as a whole? Well, the two central things that happen. One is you've got a diffusive regime, so where the total amount of stuff in the system behaves according to a diffusion process. But the second aspect is that you have non-trivial queue sizes. And so you don't have queue lengths of size 1 or 0, but you can have queue lengths of size 2, 3, and 4, okay? So why is that important in a load balancing setting? Well, it matters because you care about resource pooling, so you care about the total number of jobs in the system and how that's behaving, but also you care about how individual queues are behaving in the service disciplines that are going on there, like first come, first served, or processor sharing. And so you want to be able to analyze how the queuing dynamics locally affect the performance as well. Okay, so this sort of brings together those two aspects. And the kind of upshot of that is that, you know, in contrast to some of the universality stuff, you can begin to discriminate between different load balancing policies. So while SEM's been kind of shooting for how do I get, say, the supermarket model to be universal, you sort of attack it from the other side and saying, well, what sets of scaling regimes lead to different behaviors in these different load balancing policies, okay? So here we see a picture on the left-hand side corresponding to how these policies perform compared to like a central queued non-dispatched model. So that would correspond to just being along the x-axis there. Now we plotted the join the shortest queue model in the NDS regime here, and the idle queue first policy. Oh, I can maybe do the laser pointing my finger, I'm realizing. Anyway, so what we see is that because that join the shortest queue line is not at the bottom there, we see there's some gap between join the shortest queue and running a central queue within the system. And if we look at the idle queue policy, we also see that there's some loss due to the fact that you are only getting information about one idle queue within the system. And so you can begin to discriminate between the different load balancing policies and get some idea about their performance. Okay. The figure on the right-hand side here is quite an old paper from Bonomi. I think it was one of Ward Witt's colleagues in the 1990s. And he was analyzing the behavior of join the shortest queue. And this is very much a pre-limit model, like just a few queues, I think 2 even. And he found that if you look on the x-axis there, I have the variance of the service time. On the y-axis, I have the response time, how long it takes me to get jobs through the system. And we're looking at a processor sharing queuing discipline, okay? And he compares 2 different models. One, join the shortest queue, and the other one is least workload, essentially. And essentially, what you see there is that the shortest workload policy is not insensitive. It's actually quite sensitive to the variance in the service time distribution. Whereas you can see in join the shortest queue that it's insensitive, that actually the variance doesn't matter in terms of determining the performance of the system. And that's something you can observe in the MDS regime because essentially the queue size behavior becomes reversible and thus insensitive. And so you can begin to understand how the queuing behavior at the processors impacts the performance. Okay. So the kind of takeaway from that first part is that I think, universality of these policies is a great part of the story. And if the system's under-provisioned or even over-provisioned in heavy traffic, it's giving you a lot of information about the optimality behavior, how you want to go about provisioning the system. And so that's the kind of story that comes from the universality message. Whereas when we go to NDS, we're beginning to look at how the different performances of the policies apply, and it really stretches out and exacerbates those behaviors so you can understand the differences. Okay. So I think 2 kind of complementary messages there. The second part I was going to briefly discuss, like I said, is not something I've worked on specifically, though I've spent most of my PhD working on reversible queuing systems. So I think it's just fascinating the kind of line of work that's going on in terms of redundancy scheduling, reversibility, and product form. So the kind of classical queuing theory and product form queuing theory, going back to sort of BCMP and Frank Kelly, is that you can write out the stationary distribution as a product of simple terms. You basically take the product as you go along the set of customers at the queue, and you look at the ratio between the arrival rate of that customer class divided by the service rate to the position it is in the queue. And that's what this formula is at the top. Okay. The fantastic thing about the redundancy scheduling kind of literature is you keep that same exact structure. Now, in the picture here, I think I can click on this so you can see. The first queue, I've just ranked the jobs in the order that they've arrived. So the left-hand side is the queue with the earliest arriving job here, and then the second, third, and fourth, then the fourth over here, sixth, and seventh. And we've done some redundancy scheduling, so we've allowed the jobs to be repeated. So you can see that job 5 here has been repeated at 2 of the servers. And you can write down essentially the same formula that you'd expect from the top here, but in the case of this more complex model with redundancy. Essentially, you just product, you go along the customers in the queue in the order that they arrived, and then just keep track of that ratio, the arrival rate divided by the service rate associated with that position. So here we end up summing up the service rates. So once we're getting onto the fourth job over here, we're summing up the service rate of the Q1 and the service rate of the Q2 here. Okay, it's actually quite a simple formula, and it's originally due to this paper of Bresner, Kreil, and Krasinski in 1995, and I think there's been this kind of thread of work with Ivo Adan and people like Ivo Adan and Gideon Weiss working on it that's kind of brought this through, and then there's this kind of breakthrough paper in 2016 with Kirsty Gardner, co-authors including Moore, Harshal, Ballister, where they kind of really make the connection between this and load balancing systems and how it can improve performance and you can analyze performance with it. And as Sam pointed out in his talk, there's a great review paper by Gardner and Reiter, which I thoroughly recommend. So I wanted to just kind of discuss about that area because I think there's a lot that can be done there that hasn't been done. So there's a whole raft of information about product form, queuing networks, reversibility, and the properties associated with reversibility. So that product form structure opens up many possibilities, of which Sam has discussed a very important one in kind of resource pooling and heavy traffic regime. But there are a number of different ways that resource pooling can come in when we've got scheduling in different aspects. So one is the kind of product form structure can play well with the resource pooling behavior. And so, so paper of Can, Kelly, and Williams looks into this, how you can have independence between different independent components or different cut sets of the scheduling constraints, which is something that very much led into work with Yuan Zhong on scheduling and heavy traffic behavior in switches, and Caesar also, looked into that kind of behavior in the context of max weight. So there's a lot of structure there that can be used to give intuitions about behavior. Reversibility and insensitivity that I discussed before, only the mean matters in terms of the average behavior of the system, is something that can happen in reversible systems. That's something that's investigated by Thomas Bonald and Celine Compter, who was mentioned at the beginning. And Jonathan Anselmi, I've spoken to a fair bit about this in terms of you can use that as a way to, as a mechanism to have, say, timeouts rather than replication. So you take a job, you let it run from out of time. If you think it's taking too long, you replicate it and send it to another server and cancel the job at its current server. So if performance of jobs is an issue with the servers, then it's a good idea to start considering that idea as well. Okay. But there's still kind of open issues around this. So Sam mentioned Dirtsia Yester working on this, and there's a great paper by Anton Ayester, John Curie, and Verloop, where they look into the stability analysis of these systems. Now, if everything's exponential, everything's kind of great and everything works fine if it's independent exponential distributions. But imagine I have a redundancy scheduling system like I have in the top, where I just replicate everything into 2 queues. And let's suppose now the job sizes are identically distributed but not independent anymore. In that case, we're going to basically lose half of the capacity region because we're essentially going to get a service rate of 1 rather than the service rate of 2, which is the minimum of 2 exponentials. And so there are questions around the stability of these systems. I think that's something that will probably go away with a small number of tricks for dealing with the problem that two servers could be serving the same job. But there are definitely open issues around the stability analysis that then need to get resolved. One idea around that could be, for example, from reversibility systems, the idea of like trunk reservation, the idea that you have reserved amount of space to kind of, say, randomly choose a job and then make sure you don't get 2 servers serving the same job. Finally, the point I'd make is that one of the advantages of quasi-reversibility and quasi-reversibility in product form is that you can have multiple job classes and they can be routed and rerouted through the system. And I think that's one of the things that, like in the parallel server literature, doesn't get dealt with as much as it maybe could. And I think that's partly because it's an extremely hard problem, because if you see the picture here at the bottom, this is the kind of what a job looks like on a high-performance computing platform. Here is a Cholesky decomposition, where you take a matrix, you want to do the Cholesky decomposition. It consists of a bunch of low-level computations that you do on the matrix. And so what you get is quite a complicated branching and merging behavior of each job. And I think that's kind of maybe in a few years' time, I'd hope that that'd be the kind of area that more people in the community are beginning to kind of address and attack with some of the techniques we're beginning to develop at the moment. Okay. And, you know, one final thing to say as a discussant is, you know, a massive thanks to Sem, not just for this talk, but for the great work that he's performed over the years in the area. I think he's really been a fantastic contributor and someone to look up to in the community. Also, thanks to the APS organizers, Ramiata, Tondika, Itai Gervich, and Rhonda Reiter. And also for Snap, which I think is just a fantastic initiative that's really kind of brought lots of people together in the community. So I think a big thanks to Siva Mulguri, Debanka Mukherjee, Wayna Wang, and Christina Yu. So, okay, and that's it. Thank you. And now it's questions for Sem.
The floor is open for questions. Feel free to directly unmute yourself and directly ask questions.
Okay, this is Yash. I have a question. Has there been any work on large deviations analyses of the kinds of systems that you spoke of?
That's a great question. I believe there would be some large deviations results probably for the basic join the shortest queue policies. Although right now I cannot produce a specific reference. Maybe some of my co-authors knows, but there I would expect that to be the case. For the other scenarios, I'm really not sure. So yeah, this is, I think, really a question to everyone. I would expect so, but there's not that much, I think, and I think it would definitely be interesting to really further consider that.
Just as a comment, I think Amarjit and his co-authors have some results on large division. If Amarjit is in the audience, maybe he can give some more references or something. Yeah, that's the only work I know.
And another line of work is on max weight scheduling. Large deviation for max weight scheduling was done by Xiaojun Lin. I don't know if JSQ follows as a special case of that.
Yeah, it would be interesting. Yeah.
Sorry.
Sam, this is Vijay Subramanian. Thanks for a nice talk. I had a quick question. There is a set of work that Alexander Proutier with other co-authors has done with the graphs and scheduling with neighbors. Do you know how, could you tell me how that fits in with the rest of the literature and that? Is it a sort of a different track or?
So my guess would be, if it's the work that I think you're referring to, that it's more on the scheduling side, that there are queues associated with the various vertices in a graph, and that there are constraints as to which vertices can be activated simultaneously. Is that what you're referring to, Vijay?
Yeah, I think it's that, plus also the jobs arrive and you can send it to a queue that is neighboring or not to be serviced in some, there is some relationship to the kind of schemes that you were describing. So okay. That's what I was trying to, these are two, one is with Ganesh and others, and then other one is with Se-Young Yoon. I think these are all in Sigmatrix from the last 10 years roughly. Yeah.
Okay, so so then there would probably be some relationship. So I'm not aware of the routing part. So I've seen, I think, some work of Alexandre where it's more sort of scheduling with certain exclusion constraints. I think there are some connections between sort of the scheduling and the routing problem. Like, for example, look at join the shortest queue in the routing context versus serve the longest queue in the scheduling context. Mm-hmm. That I think is some similarity. I think what Siva was alluding to, that Maxway join the shortest queue, there are some natural connections there, but I'm not specifically familiar with that with that paper feature, so I should probably look at that. One recent paper that I did see was on join the shortest queue more in a wireless context, where you can route a job. It has like a default destination, but you could also route it to one of the queues in the sort of geographical neighborhood. And what does that mean in terms of how often do you go far away to find a shorter queue in a spatial context? So that might also be somewhat related. I think that's work of Don Towsley and co-authors, which was also presented at Performance last week.
Oh, thank you. Yeah.
But thanks for the reference. I should check.
Well, I can email it to you separately.
It would be great. And otherwise, I should chat with Alexander. It's been a long time since I spoke to him.
I have a question also.
Mm-hmm.
Hi, hello Sam. It's Anastasis Giovannidis from Sorbonne. My question would be, you schedule, for example, some depending on the cases, and you keep the policy fixed. So you keep either join the shortest queue, or you have d equal to or d higher.
Mm-hmm.
So I was wondering if you would, for example, start doing scheduling depending on the state of your system. So, for example, you could keep join the shortest queue for some state, and then change for d equal 2, d equal 3, etc., depending on how many servers are occupied or how much is the length. Is there any direction taken like this?
So I have not seen quite something like that, but I think it's a very interesting suggestion that sort of depending on the queue state, that you are prepared to maybe collect more state information to make the right decisions. It reminds me a little bit of maybe also what Neil was saying, that depending on the load scaling, that you may want to use a little bit more information to improve the performance and maybe match join the shortest queue. So if you somehow translate loads to typical queue lengths, I could see that there is some similarity there, that except that you do it not based on the load parameter, but the actual state of the system. So I think that would be very interesting indeed. Yeah.
Okay. But there is no such work done until now.
Not that I'm aware of, but
Okay.
There might very well be others who have seen that. So if anyone else has maybe seen something specifically along these lines, then please feel free to step in. But I haven't, to be honest.
Okay. Okay. Thank you.
Just from my reading of the redundancy scheduling stuff, I think you can change the service rate based on the number of jobs in the system, but that's different to changing the dispatch rule. So there are things where you can, and I think you can have reversible systems where you can change the arrival rates a bit as well. So it might be within that framework it's possible to, but that's different to the join the shortest queue D type policies which you're talking about.
So I have a question about, so I think for the second part of your talk, you were talking about this compatibility. So if I understand it correctly, the rate of the service or the service speed is mostly determined by what type of server is providing the service. So I was wondering, from two aspects, from the application aspect, you are mostly motivated. Does it make sense that the service time depends on both the class of jobs and the type of server? And if you take that type of service time into consideration, would that substantially complicate the theoretical analysis of the system?
Yeah, that's an excellent question. So, so the way I presented the model now, it is that the service speed only depends on the server essentially, and the job type is either compatible, yes or no. So it's like binary. In the, I think, very final bullet on the final slide, I was trying to, I think, describe the scenario that you're describing, where we would have a service rate for a job that depends both on the type of the job and the server. And I think that gets even closer to some of the issues that need to be captured in data center context. I think it does make the theoretical analysis harder, that scheduling, like intra-queue scheduling, becomes part of the problem. And that, I think, is a new element that hasn't been addressed so much in conjunction with load balancing. On the other hand, if we think of scenarios where most of the jobs would find zero delay, then perhaps intra-queue scheduling is not such a big deal. So I think, yes, theoretically it would make the problem much harder, but if we can somehow get into regimes where queues would still only be of size 1, that perhaps that could be tackled as well. So yeah, great point.
Thank you.
If there are no more questions, let's end the Markov lecture by thanking both Sam and Neil.
Thank you, Siva, Bankur, Christina, Weina, again for hosting this. It's wonderful. Thank you very much.
Bye, everyone.
Thank you.